Hello, wonderful people! Here we are at the very end of chapter 32, Electrostatics 32.7, Charge by Polarization. So, ways to charge. There's the big three, charging by friction, by contact, and by induction. We've covered those. And today's the fourth one that doesn't get talked about as much, charge by polarization. A reminder, there's the charging by induction situation. You start off with the metal balls in contact. You bring in a charged rod that pushes the electrons away from the charged rod, so they go to B, and A gets the positives. Then you take the charged rod away. Oh, I'm sorry. No, then you separate the balls in the third picture, and then you take the charged rod away, and now you have a bunch of charge on B, and the opposite of the rod, and the opposite charge on A. Similar idea is what we're going to do today. Let's start with some basics. So I've got a positive charge and a negative charge. The arrows show you the direction of the electric field. So we always draw the arrows going away from a positive charge and into a negative charge. This way, if everybody plays by those same rules, then we know which way the arrows are pointing. So there's a positive plate and a negative plate in the blue, and the arrows are showing you the way that we normally draw the lines of charge. So down below, I've got a water molecule. You should remember from chemistry class, water is H2O. And if you remember, the H's aren't exactly opposite each other. They kind of attract on one side. So what does that mean? I'm going to read from the top. A polarized molecule is one in which the negative charge is primarily on one side of the molecule, while the positive charge is primarily on the other side. Water is a good example of a molecule which polarizes easily. In water, the two hydrogen atoms each give up an electron to the oxygen. The atoms bond to create the shape illustrated below. Ta-da! Thus, the left side of the molecule, containing the oxygen nucleus, is more negatively charged. The right side of the molecule, containing the hydrogens, is more positively charged. Why? Because they gave up an electron to fill the oxygen's outer shell. This tendency for charge to separate in a neutral molecule is called polarization. So please note, the oxygen and hydrogens all have a total of 8 protons and 8 electrons between them all. So there is no positive or negative charge on the molecule. It's just that since the hydrogens are bent over to one side and they're a little bit more positive, that means that that side of the molecule, the right side, is more positive, and the left side of the molecule is a little bit more negative. Are you with me there? That's more than half the battle so far for today. So up top, I have 3 molecules, acetic acid, ammonia, and ethanol in the one picture. And then all the way on the right, I have another ammonia. So you can see I've got pluses and minuses on each side of the acetic acid molecule. The negatives are by the oxygen. On the second one, ethanol, I'm sorry, on the second one, ammonia, the charge is negative as on the bottom by the nitrogen. Oh, I don't have a positive up top. I'm sorry, I should have drawn that in. And then the third molecule, ethanol, has a positive side and a negative side. And then the fourth one is the same picture as the second one, ammonia. If you see where it's got that lowercase delta, the Greek letter, and then a minus and a plus, we put that Greek letter delta in there to remind everybody that this is just a fraction of a charge. We're not talking about a whole electron. We're just talking about a little bit of charge. So it's a little bit positive on the bottom and a little bit negative on the top. So are you comfortable with a molecule that has positive on one side and negative on the other side is what we call a polarized molecule? The total charge on it can be 0 or it could be plus or minus. But the point is the molecule itself has one end that's a little bit positive and another end which is a little bit negative. Oh, okay, so we've got positive charge on one side, negative on the other, And now here's a picture of some molecules that are all together. And you can take those polarized molecules and make a big solid object out of it. And that's what the picture would look like. This is a picture of gypsum. In the picture in the top left, that's a little chip of gypsum, a little smaller than a fist. Below that is a picture of gypsum on the surface of the planet. Those crystals grow that big out in the desert. And then on the right is a picture of a man down in a cave. Do you see the person down in the lower right-hand corner? I'm pretty sure that's in Nevada. And I used to live in Nevada, and there were gypsum mines a couple miles or a couple dozen miles away from the town that I lived in. They didn't look like that. They were just solid material in the rock. Those gypsum crystals, though, that's pretty cool. So what's gypsum? What is gypsum? Do you see right there? It says CaSO4.2H2O. So that means that it has calcium, silicon, and oxygen. And then there are two water molecules that are also a part of that molecule. Gypsum's used mainly as a fertilizer, and it's also used to make drywall and also chalk and plaster. But we're talking about drywall today. So there's the molecule. There's the, what was it? CaSO. Calciums and silicons and oxygens, where's my pointer, are all here. And then there's one water molecule and a second water molecule. So the water molecules are part of this atom, but do you see how the water molecules are between the main molecule of CaSO4, and these water molecules are attached, but they're in between. Is that making sense? So that's what it really looks like. And then over here is a picture of the geometry. So the water molecules are the little pyramids there, and they sneak in between the bigger atoms of the molecules. And it does come in sheets like this. Now, the interesting thing I want you to realize is those waters are basically keeping separate the CSO4 molecule. This is separate from that one. That's the point of this. Because now, this CaSO4 molecule over here has polarization on it. There's a positive end and a negative end. And so I just drew this molecule up as a circle. So here's a circle. It has a positive red end and a negative blue end. And the waters are in between here, but I'm ignoring the waters for now. The point is, because there's waters in between there, this molecule can just spin around anywhere it wants. And because there's the water between them, it's going to point in whatever direction it wants. It's not paying attention to, it's not close enough to have these other charges all line up. So all these molecules can spin in any direction they want. Their charges are all just pointing in different directions. So now what are we going to do? If I rub a balloon against my head and electrons transfer to the balloon, now the balloon has electrons. So there's electrons in the balloon and positive charge left back on my head. So I'm going to take the balloon with a negative charge and I'm going to put it over here next to the gypsum wall. So all these negative charges, and there's a whole bunch of them, these charges are strong enough that they reach out and pull on the positive side of each gypsum molecule. And because that molecule can spin in place, they all line up. So now, if the positives are all facing the balloon, what do you think happens? You already know what happens. You ever rub a balloon against your head and then stick it on the wall and it stays there? That's what happens. So why does the balloon stick to the wall? Because the negative charges on the balloon are attracted to the positive charges, and the positive charges are closer. So this whole thing ends up having a positive charge on the right side of it and a negative charge on the left side of it, which allows the balloon to stick to the positive charges in the wall. Amazing. So here's another picture of the same situation. I've got the negative plate here and the positive plate here, and the material in between the plates has polarized molecules that can rotate in place. And so the positive sides are pulled to the negative sides are pulled to the positive. So all the molecules in this little material line up. Here's another example. I've got a charged rod with positive charges on it, and this material here, all the molecules stay in position. And there's no electrons moving over to this, it's the molecule itself is flipping so that the negative side is towards the positive. And you get an attraction there. Another way, the same picture, the negatively charged balloon and all the positives in the wall. And I've got these little, that's now the letter sigma, which is another letter they use to show partial charges. And because of the positives are on the right, there's a net electric field going this way to attract the balloon so it can stick to the wall. Yeah, that's the whole show. Charging by polarization. This material is made of polar molecules, and these molecules are able to rotate in place. Not all materials can do that. Some can, which is why it's easy to stick a balloon to a wall at home with the gypsum wallboard. So there's a couple homework questions, and then that's the end of the chapter. But the next chapter is going to be more about electricity. So we're going to try to squeeze 3 chapters into the next 2.5 weeks, and that will be the end of the school year. And believe me, this learning about electricity and just knowing the basics of how electricity works, this will be very useful for the rest of your life. I promise. Because everybody, you plug in your phone every night, and there's a million other things. It just makes life easier. Trust me, you'll be glad you understand this stuff, especially when you have to buy a house or rent an apartment. Oh, yeah, definitely. Okay, good luck. Thank you so much. Bye bye.